In this lecture, we continue our study of multiple integral. Okay, the first result we'll talk about today involve an important concept, the so-called Jordan domain. Okay, so a bounded subset of Rn is called Jordan domain. If the boundary has Jordan content 0. Okay, this is a definition of a Jordan domain. So Jordan domain is the basic domain of integration in our integral theory. Okay, so we have the theorem below. Suppose D is a Jordan domain in Rn. And f is a continuous, f is a function defined on D. Real valued function, bounded. Our function always bounded. So E is the set of discontinuities of f. E is, maybe we'll write in a C. E is those point where f is not continuous. E is the set consisting of all the discontinuous points of f. Then, if E has Jordan content 0, our conclusion is that f is integrable. If E has Jordan content 0, then f is integrable. In our notation, we can write f belongs to the Rd. Rd is the set of functions which are integrable over D. Okay. So we prove this theorem. What this theorem means? So this is our D. The function defined over D, the bounded function f defined over D, is this function integrable depending on the discontinuous point of f. Previously, we have proved that if a function has a function defined on a rectangle has a discontinuity of Jordan content 0, then the function is integrable. Now, this theorem is the generalization for that theorem. That theorem only dealt with functions defined over rectangle. Now we consider general subset D. Okay, so this is the important theorem we will need later. So to prove this theorem, we consider because we are integrating over a general subset, we need to take a rectangle enclosed D. Suppose this I is a rectangle containing D. Take a rectangle I containing D and consider FD, the zero extension of F. So the discontinuity of FD we denote by E star. That is E star is the set where FD, the zero extension, is not continuous. Okay, we did consider this E star. Then FD is integrable. So we know that F is integrable if and only if the zero extension is integrable over the rectangle containing D. And now we apply the result on the integrability of functions defined over rectangle. We see that this is equivalent, maybe not equivalent. We have not proved the equivalence, but we only need this. Okay, actually they are not equivalent. So to prove that f is integrable over D, we need the zero extension to be integrable over the rectangle I. Okay, this step is equivalent. But to ensure that fd is integrable over the rectangle I, we need E star has Jordan content 0. Okay, if E star has Jordan content 0, then the zero extension fd is integrable over the rectangle I. And then by definition, f is integrable over D. Then proving our theorem. Okay, now we let E star be the discontinuity of fd. Then we declare that E star is a subset of the boundary of D, the union of the boundary of D and E. That is, fd is discontinuous. Fd can only be discontinuous at those points either on the boundary of D, or at some point in D where f is not continuous. Okay, so once we can prove this result, since the right hand side of this inclusion all has Jordan content 0, so the left hand side is that as a subset of Jordan content 0 set must also has Jordan content 0. Therefore, the theorem is proved. Okay, so we only need to prove this inclusion. So to prove this inclusion, we assume that a point not in the right hand side, if a point denoted by A does not belong to the right hand side, then we have two possibilities. Either the point is in the interior of D and f is continuous, at this point. This is the first possibility. Or the second possibility is that A contained in the exterior of D. If a point not belongs to the boundary of D, if a point A not belongs to the boundary of D, then it can either be an interior point of D and an exterior point of D. Okay, you can only be here or here, inside D or outside D. More precisely, it can only be an interior point of D or an exterior point. So, if A is not contained in the union of the boundary of D and the discontinuous set E, then either A is an exterior point, or if A is an interior point. But if A is an interior point, because F is not continuous, A is not belongs to E, then F must be continuous at A. So A can only contain in we can only have these two cases, this case or this case. Okay, so we consider both cases. So in case 2 is simpler. So A is here, A is in the exterior of D. Then we can take a small neighborhood of A, so that the neighborhood is contained in the exterior of D. But in this small neighborhood of A, fd is 0, identically 0. So near this point A, f is identically 0. Therefore, FD is identically 0. The 0 extension is identically 0 in a neighborhood of the exterior point D, A. So FD is continuous at A. Therefore, FD is continuous at A, so A cannot contain E star. So in the second case, we conclude that A does not belongs to the E star. Okay, this case is simpler. But for the first case, it is also similar. So suppose A is an interior point. A is here. Suppose A is here. I change the color. Suppose A is here. Then since this A is an interior point, we consider case A. A is an interior point and F is continuous at A. So because A is an interior point, we can take a small neighborhood of A. The small neighborhood contained in D. For A, there is a delta positive such that the delta neighborhood of this A is contained in D. So in this neighborhood, our 0 extension is identically equal to F. But F is continuous at A. Therefore, FD is also continuous at A. So in this case, A can also not belongs to E star. So we have proved that if a point A does not belongs to the union of the boundary of D and E, then this A will not belongs to E star. So this proves that E star is a subset of the union. So E star has Jordan contained 0. Okay, so this proves our theorem. Okay. Now, when we introduce the set of has Jordan contained 0, we have proved that the graph of a continuous function has Jordan contained 0. Okay, but we know that continuous function is a subclass of the integrable function. And a function is continuous, then it is integrable. But there are integrable functions which are not continuous. Okay, so we will generalize the result to the following case. Another theorem. D is bounded subset, and the F is integrable over D. Then the graph of F has Jordan contained 0. Okay. The graph, do you remember the graph? The graph is the set X, F, X. X belongs to the domain of definition. This is a subset of Rn plus 1. Okay, so this is the graph.